Okay, welcome to Chapter 6. We've made it through Chapter 5, where we learned how to do a little bit of dynamic optimization. And if I haven't scared you away yet, that's a good thing, because I hope that Chapter 6 will make things a little bit easier for you, a little bit easier to understand. So, really, we're just picking up where we left off, sort of, with Chapter 5, because last time we saw how to maximize an agent's utility function over two different periods. We had period T and period T plus 1. And we learned about that consumption savings problem with the decision that we had to make. Do we consume more now, or do we save today to be able to consume more a little bit later? And we learned about the Euler equation, which is a necessary condition if the household's optimizing their consumption and savings decisions. But it's not a consumption function, and it doesn't indicate how much consumption in the present and future household should have if it's optimizing. Rather, it tells us how much relative consumption the household should have as a function of the real interest rate. Now, as I've said before, this is the cornerstone of like all macroeconomic analysis using micro-founded models. And the reason that we're even using micro-founded models is because we're like, okay, a macroeconomy is made up of a bunch of tiny households. So if you model the individual household and then aggregate it up, you're now getting a model of the macroeconomy. And you're doing it from a perspective of how individual people are choosing. So today we're going to be learning about indifference curve analysis to see what the optimization looks like on a graph. And hopefully if you can see it on a graph, it'll make a little bit more sense. Now, if you've had intermediate microeconomics before, then this is going to be nothing new. And if you haven't had intermediate micro and you end up having to take it, then when you take that, that will be nothing new. So either way, at some point, you're going to go, hey, this is nothing new. So if we remember with the budget constraint, right, we had the constraint that basically said the source of resources or the source of funds has to be equal to the use of funds. So what we're going to do is we're going to graph the budget constraint first, and we're going to just do a nice like two-dimensional graph with current consumption on the horizontal axis and future consumption on the vertical. And then we're going to plot out our budget line, and that gives us a graphical representation of the intertemporal budget constraint. And that budget line shows us that the scarcity the household faces when they're trying to optimize. So it's going to show all possible combinations of current and future consumption that will max out that constraint. Because remember, the constraint is equal to C sub t plus 1 equals 1 plus the real interest rate times y sub t minus C sub t plus y sub t plus 1. Now, without this utility function, to see how the household's optimizing, literally any point that lies on the budget line could be an optimizing point. We need a utility function to tell us which point is the utility maximizing point that lies on that budget constraint. So this is the budget constraint. It says the budge constraint. It's like I always find like one or two errors in all of my lectures. And whenever I'm like, oh, yeah, I fixed them all. I fixed them. Great. And I go back and realize I missed something else. So we have our budge constraint here. And what I have in the pink is the actual budget line. And we can see when C sub t is 0, right, if you go back to the budget constraint, let C sub t be 0, well, you'd have CT plus 1 equals 1 plus the real interest rate times current income plus future income. And that's what we have right here. Now, when C sub t plus 1 is 0, well, we go back to the budget constraint. That's 0. Okay, so it's basically this. It's just all this stuff here on the right-hand side is equal to 0. Cool. Well, what do you do? Well, you probably have to solve for C sub t then. And that's what you'd end up doing. So this is our budget line. And we have this endowment point. What's this endowment point? Well, that is the point where we have our current income and our future income. Now, we can have lower current income and higher future income, as again, it could be literally a continuum of points along this budget constraint. But we'll just say that this is the particular endowment point that we're going to be looking at. Now, if we consume everything today, well, then we've got today's income plus tomorrow's income divided by 1 plus the interest rate that's available to spend. Why is that? Well, basically what I'm doing is I'm borrowing from tomorrow. I'm borrowing from my future self if I want to consume everything today, because this budget constraint isn't saying I have to consume everything that I earn today and then everything I earn tomorrow in those two periods. I can save, right? So if I'm saving, well, I don't consume everything that I earned today, and it frees me up for a little bit more consumption tomorrow. Additionally, I can always borrow from tomorrow. So I can borrow, and when I borrow, I'm consuming more than I earned today, but then I got to pay it back tomorrow and consume less. So that is really the idea of this budget line. And then that endowment point is the endowment that we have in the form of income. So I have the two intercepts here. I've got the CT plus 1 and the CT intercept, which I kind of already explained. So we have a budget line, which gives the intertemporal budget constraint for the representative agent in our model. And it's really giving us an idea of the trade-offs between current and future consumption. Think of it as the marginal cost of consumption today in terms of tomorrow's foregone consumption. Now, if the line gets steeper, that means we have to give up more future consumption to consume more today. Thus, if the line gets shallower, current consumption becomes less costly than future consumption. And it leads to a most useful conclusion about the slope of the budget line. The slope of that budget line is the real interest rate. And the higher the interest rate, the more future consumption will cost in terms of current consumption. So a higher interest rate induces you to save more of your earnings and consume it tomorrow instead of today. So from the Euler equation, remember we had that u prime of CT equals beta times 1 plus the real interest rate times u prime of CT plus 1. This gives us the relationship between current and future consumption. It was a function of time preferences in the interest rate. And if the interest rate were to go up, if it were to increase, the agent would be induced to save more today to consume a lot more tomorrow, which then brings us to the slope of the budget constraint. Well, the slope of the budget constraint is really 1 plus the real interest rate, because the real interest rate serves as that deciding factor between current and future consumption. So the marginal cost of consuming an additional unit of consumption today is 1 plus the real interest rate. But wait a minute, it's downward sloping, so why would that be? Well, if the interest rate goes up, you want to save more today and consume more tomorrow. So the interest rate increasing leads to negative changes in consumption patterns, and it reflects the trade-offs that we're facing in economics. So we multiply 1 plus the real interest rate by negative 1, which gives us negative 1 plus the real interest rate. Okay, so let's move on to the utility function next. So the utility function is a two-period function given by u of CT plus beta times u CT plus 1. And the graph of this is going to have different indifference curves. And these indifference curves are exactly like what you saw in micro, and each level curve is a different level of income. So the more income we have, the higher the indifference curves are going to be. And we have a couple things we need to specify about these indifference curves, but first let's just take a quick look at it. So these indifference curves right here represent different levels of utility or different levels of happiness. Now, on, say, the indifference curve u sub 0, whether I consume this much today and this much tomorrow, or if I consume this much tomorrow and this much today, my level of happiness is going to be the same. And if I wanted, say, a higher level of happiness, say U1, well, that would be here. Literally any combination of consumption that satisfies this blue curve gives me the same level of happiness. So again, whether I'm over here or I'm over here, the amount of utility I derive is the same. If I go up here to U2, well, I've got more utility here than I do in U1 or U0. But again, any combination of points, and it's a continuum of points that satisfy this green curve gives me the same level of utility or the same level of happiness. So why would we have lower levels of utility if we could just be on higher levels of utility? Well, that's where the budget line comes in, because we'd like to be at the highest possible level of utility. All right? When you think about economics, right, when they tell you at the very beginning of like principles of macro or principles of micro, the whole point of economics is that we have unlimited wants and limited resources to satisfy those unlimited wants. Well, here we have unlimited wants. We obviously would want incredibly higher levels of utility, even higher than U3. U3 is better than U2, 1, or 0, but, I mean, everything's better than U2. But, there could be U4, U5, U6, whatever, all the way U up to infinity, U infinity. Could be all the way up here. That would be better than being down here. We get to consume more today and more tomorrow. But if we want to be up here, that's great, only if our budget constraint allows us to be up here. So let's say of these 4 utility curves, these 4 indifference curves, or if you've taken Calculus 3, these 4 level curves. Of these 4, let's say one of them, the budget constraint gives us one of them that is feasible. Well, not just feasible, but also that maxes out that budget constraint. How do we know which one that is? Well, we don't just yet. We will find out soon, though. Okay, so for this utility function, let's say we were to hold income constant. Well, if we're holding income constant, you can sort of think of it as like we're on one of these curves, right? I really should have said like if we're holding utility constant rather than income. But if we were to consume more today than tomorrow, C sub t goes up. Now, if that happens, right, if we're on here, let's say I'm at U0, C sub t goes up. That means I consume more. Let's say I was consuming over here, now I'm consuming all the way over here. Well, if I want to stay on this indifference curve, I was consuming more originally tomorrow, but if I want to consume more today, I have to consume less tomorrow. I got to give up some CT plus 1 in order to be able to consume some CT today. So I got to give up future consumption to maintain the same level of utility or the same level of happiness. So if I have that utility function, and you don't have to do this, so don't freak out and go like, oh my God, it's all this math. But if we took a total derivative of this utility function, we would get, well, equation 4 right here. What is this? Well, we're looking at the change of utility with respect to C and the change of utility with respect to CT plus 1. But I got to do my partial derivative of U of CT and CT plus 1 with respect to CT, and then with respect to CT plus 1. And then if I want to hold the level of utility constant, what I'm doing is I'm letting this du CT plus 1 be equal to 0, meaning we pick one indifference curve and we stay on it. Doesn't matter which one, because regardless of the indifference curve that we're on, it's going to be the same. So we know that this utility function exists in R3, which means we can move in really 3 different directions. We can move in the CT direction, the CT plus 1 direction, and then the U of CT and CT plus 1 direction. So 1 and 2 are the inputs, 3 is the output. Or 1 and 2 are the independent variables, 3 is the dependent variable. So if we were to hold one of these directions constant, it means the change in the direction of that dimension needs to be 0. So I'm holding 3, 0.3 here, constant. I'm allowing for changes in CT and CT plus 1, but there is no change in U of CT and CT plus 1. So doing that, I set this total derivative equal to 0, and that keeps me on a fixed level. And now I want the slope of that indifference curve. Okay, so I get dCt plus 1 over dCt, right? The change in CT plus 1 over the change in CT. So if I want to get that on one side and then have everything else on the other, well, I got to do a little bit of math. divide some stuff, subtract some things. You don't really need to know how I'm doing all this stuff, but boom, let's look at equation 8 here. All right, in equation 8, the left-hand side, dct plus 1 dct. What is that? Well, think d as in like change. So the change in ct plus 1 over the change in ct. Slope, right? The change in y over change in x. This is ct plus 1 would be like y. The vertical ct would be x, the horizontal. Change in y over change in x equals the marginal utility of current consumption divided by the marginal utility of future consumption. Well, this marginal utility here, we've learned in the previous lecture, marginal utility is always positive. So if marginal utility is always positive, this numerator is positive, this denominator is also positive, but it's negative of this over this. So a negative of a positive divided by a positive is negative. So it's telling me the slope of any indifference curve is always going to be negative. So to keep the same level of utility, in order to consume more today, meaning you save less for the future, if you're saving less, you have to give up consumption from tomorrow, which is the consequence of saving less. If you want to consume more tomorrow, you have to give up some consumption today, which is the consequence of saving more. So we have downward sloping indifference curves, always. Now, when the agent's maximizing their utility subject to a budget constraint, they're finding a tangency point of the constraint with that utility function. So if you've taken Calculus 3 and you remember doing constrained optimization with Lagrange multipliers, we're basically doing that here, except instead of using the Lagrangian, what we're doing is we're taking the constraint and we're substituting it into one of the independent variables. You get the same set of answers at the end either way. So we could do this with a Lagrangian if we wanted to. I choose not to. It's easier just to do some substitution. But recall that constraint can't get violated, hence the name. It's a constraint, right? So that utility function requires that all of the budget be maxed out, right? Because if you're not consuming, you're saving. Okay, so you're either consuming or you're saving, and you don't have a third option there, right? Because you either spend it or you don't. If you don't spend it, you're saving it. Boom. So it's like there is no third option here. Because there's no third option, regardless of how you spend that money, that budget's getting maxed out every single period. The budget's also being satisfied every single period. So we're spending no more and we're spending no less. This allows us to achieve the highest utility possible. So the budget line will touch one of the indifference curves at one point and only one point. And this is what's known as a point of tangency. And at that point of tangency, that's when the agent is maximizing their utility. So let's say I plot out U0. I know I changed the colors, sue me. Plot out U0, and then this budget line gives me a point of tangency where we have C star of like CT plus 1 star and CT star. They're starred because these are the optimal levels of consumption for today and tomorrow. So if you see anything starred here, that's always like an optimal condition, right? So this is the optimal consumption bundle or the optimal consumption sequence over time for this utility function given this particular budget constraint. So it's an optimal consumption bundle, or like I said earlier, an optimal consumption sequence. And because this is dynamic, it's really like a sequence of consumption. So now that we know what that looks like, let's maybe change some of the parameters and see how everything adjusts. And, it's really like one of the cool things about economics. You kind of like screw with the optimum or you screw with the equilibrium. You disturb it, you jitter it, whatever you want to call it. And then you watch how everything kind of adjusts. And doing it in dynamic macro is like really cool because you got all these moving parts and you get to change one of them and see how like all the rest kind of like domino effect or like if you ever see videos of people like in the studio, recording music or whatever, and there's like that giant like switchboard thing with like the little slides and you flick one of them and they all kind of like wave. It's like that. It's really cool stuff. So moving onward. So income matters. Pretty obvious that income matters. And it matters in more ways than you might initially think. Because there are like really three incomes for us to be thinking about. There's the first period income. There's the second period income. So there's like today's earnings, tomorrow's earnings, and there's lifetime income. Now, it's really just a discounted sum of the first two, and this is not really a third type, but like, whatever. Like, sue me. Like it says, make your intermediate macro class, make it better than mine. And if you do, tell me how you did it. That'd be great. So let's say current income was less than current consumption. What does that mean? Has there ever been a time in your life when consumption's greater than what you're earning? It probably is right now while you're in school, because you're probably taking out student loans. I know it sucks, especially when you're like, I want to go to graduate school and I want to follow my dreams, and then you end up 6 figures in debt. That's not fun. I don't know how I'm ever going to pay that back. Which means if your current consumption exceeds your current income, a good way to think about it is that you're borrowing from your future self. I mean, really, technically you're borrowing from somebody else right now, but you're borrowing against your future earnings. Thus, you're kind of borrowing from your future self. And I'm sure your future self's really going to love you when it's time to actually start repaying your student loans. I hope to God you don't have student loans. If any of you don't have student loans, that's excellent. I'm so happy for you. Either way, we have a case where CT is greater than YT. And on the graph, that looks like what we see in this kind of tealish green right here, right? Because if you look on the CT axis, CT star is greater than YT. Now, the only way to make that happen is if CT plus 1 is less than YT plus 1, because you consume more than you're earning today, but then you got to pay it back tomorrow. So you're borrowing against tomorrow's income to be able to consume more today, even though we end up consuming less tomorrow, which really sucks for tomorrow. But again, that's for future us. That's not for current us. So we're going to let those future us, let those poor slobs deal with it. We don't care. Now, the same can be said for when we save today and spend it tomorrow instead, right? So let's say, you're in your mid-20s up to probably your mid-50s or so. You're probably going to be saving a lot more than you're spending, right? So you're spending less than what you're earning because you're like, at some point I got to retire. And I don't want to be working until I'm 95 years old. I don't want to work until the day I die. That's going to suck. Although if you hate your job, maybe that would be kind of cool because then your coworkers who suck, you're like, ha, sucks to suck, I'm dead. In that case, what we would have is something more like this, where current consumption is less than current income, but because we're consuming less than we're earning today, we get to consume more than we earn tomorrow. So say this is pre-retirement, right? CT and YT, this is pre-retirement. CT plus 1 and YT plus 1, that's during retirement. Either one of these, technically speaking, would satisfy the constraint. Now, of course, is this like an optimal thing? Because, we've got this indifference curve here. Either way, we have a situation where current income doesn't need to be equal to current consumption. So the lifetime budget constraint says that lifetime consumption needs to equal lifetime income. That's it. So it's basically saying you don't get to die with any debt and you don't get to die with any additional savings. The sum of current and future consumption is equal to the sum of current and future income. Okay, cool. Say there's an increase in income for the agent for both periods. What happens? Well, the budget line just shifts outward. Now, before I show you what it looks like, I'm going to be adding a couple of new subscripts to this one. So there's a 0 subscript, which denotes original utility, and 1, which denotes the next utility, the higher utility. Okay, so with all that out of the way, boom. I know it's getting complicated fast. There's a reason why I'm only going to have you guys do some of the stuff and not all of the stuff. But what happens? Well, the endowment point shifts out. We now get to move to a higher level of utility because we have a higher budget constraint. Thus, you can afford more stuff. Per example, I love giving you guys examples. I don't want to keep this super abstract all the time. couple of years ago, I was working a job, and I'm still working a job, but I moved from one part of the company over to another part. And when I did that, I got a raise. I got more money. When I got more money, I was like, hey, this is great. This is awesome. I'm making more money. So what's the first thing I did? I went out and I bought a new car. Something like that, right? Why? Why did I do that? Well, because I could afford it, and it was a really cool car. I'm glad I bought it. But I couldn't have done that on the original, according to the original budget constraint, but the budget constraint shifted because my income shifted. Thus, I can buy more stuff. So an increase in income shifts the budget line out, and then we end up getting this new level of utility. This is a really nice one to draw. There are no changes in the slope of the budget line. And that's when the stuff really gets ugly. But again, I'm not really too worried about that right now. So let's talk about a change in current or future income. Let's say there's a change in future income. What happens? Well, current income stays the same, right? It's not moving anywhere. So what happens is we move from our current, or I guess our initial future income to, I guess, our new future income. And we get something like this here. Now, again, that endowment point changed, right? Because C0t and C1t and C0t plus 1 and C1t plus 1 both increased. Wait a minute. Why would current consumption increase? Well, it would probably help to tell you that, first off, this model has perfect foresight, right? There's no stochastic component. There's no expected anything. It's just, you know what your income is going to be today. You know what your income is going to be tomorrow. So if your income increases tomorrow, you know it's going to increase tomorrow. It's like going, okay, well, I'm not making very much today, but I know I'm going to make a lot more tomorrow. Screw it. I can buy more stuff today. That's cool. So the budget line still shifts out. The slope still doesn't change, though, because the interest rate didn't change. Remember, the slope of the budget curve is the interest rate. So household spending goes up because household income increased. Both current and future consumption increase as a result. But note, savings falls here because there was no change in current income. So it's a big deal to think about. The savings is going to increase when current income increases, but it falls when future income increases. Now, it might seem a little counterintuitive, but let's walk through it and understand why now. There's only saving in the first period. Savings in the second period are zero because the world ends the next day, right? There's no point in saving anything. So if current income doesn't change, current savings won't change either. So if you found out you were going to be making $1 million a year starting next year, would you save more than you were before finding out about this nice change in income? Bet you do the opposite, actually. If I found out I was going to be making a lot more money next year, and I knew with 100% certainty that was the case, I'd be like, screw it, man, I'm spending a whole hell of a lot more money today than before because I can afford to. And that's really all that this is saying right here. You expect to make more money, thus your current consumption patterns will change a little bit. Now, whenever income increases, or it's expected to increase in the future, the household wants to increase consumption in all periods. It implies that they're smoothing their consumption over time by changing their savings behavior. And if the household expects increases in future income, the household saves less, meaning they borrow more from the future, which increases their current consumption C sub t. And this happens because of diminishing marginal utility of consumption, which goes back to the assumptions about the first derivative of the utility function being positive and the second derivative being negative. The household wants to increase consumption by a little bit in response to both periods. And this is where we get consumption smoothing. And the definition of that is, regardless of changes in income, households prefer to have a more stable path of consumption. And given changes in current income or deviations in expected future incomes, households will borrow or save accordingly to maintain a stable path of consumption over their lifetimes. So if your income goes up a little bit more, your consumption really isn't going to change that much. Like when I went from, old job to new job and I bought that new car, overall my consumption patterns weren't really changing that much. even before I bought that new car, and I still, was in the new job, my consumption pattern still didn't really change all that much. I was putting a little bit more in savings, I guess. But aside from that, yeah, they really weren't changing. And the idea is whether you make a little bit more or a little bit less, your consumption is relatively going to be constant, or maybe not constant, but relatively smooth. Now, this actually leads to something known as the permanent income hypothesis. And this was hypothesized by Milton Friedman. And it suggests that only permanent changes in income will really affect the consumption or savings behavior of optimizing economic agents. This actually got Friedman the Nobel Prize in economics. It posits lifetime income matters when it comes to altering the consumption savings decisions, and agents will be smoothing their consumption over their lifetime. So the less permanent the change in income, the less they're going to alter their behavior. So if you get a big bonus, right? Let's say you get, God, wouldn't it be nice, like a $100,000 bonus or something. I can only hope one day to find a job that gives me $1,000 bonus or $100,000 bonus. That'd be awesome. But let's say, you get like a $100,000 bonus. That's huge. But you're not going to get it the following year or the year after that or the year after that. Your consumption will change a little bit, but not that much. Now let's assume you get an extra $100,000 a year every year. Your consumption is going to change a lot more. That is the main point of the permanent income hypothesis. So agents will only save if they expect their permanent income will be less than their current income. So really what we did is we just drew out the permanent income hypothesis. Kind of cool stuff, isn't it? Okay, so up until now, we didn't change the slope of the budget constraint. We just shifted it in or out. This is where we make things harder on ourselves. We're going to start changing the interest rate here, which changes the slope of the budget constraint. And this isn't as nice. I don't really like it as much. But I guess it's important to at least see what it looks like so you know. So when the interest rate changes, the budget line pivots. Hence the slope changes, right? Pivot. But there's no change in income. So the budget line pivots through the endowment point. Like this right here, right? So that endowment point that we had is that pivot point. Now, we're going to assume the household's initially saving, which means the endowment point is going to be below CT and above CT plus 1. We're going to leave that out just for a minute so that we don't crowd out the graph. But let's assume the interest rate changes. We have the following. Oh, my God. Okay, yeah, that kind of sucks. Whew. Okay. What are we doing here? Well, okay, what happens? First, we have this pink budget line. This is the initial one, right? Then it pivots to the blue. Sorry about that. It pivots to the orange. It doesn't pivot to the blue. It pivots to the orange. So this is the endowment point right here. And it pivots here. Now, when it pivots, okay, well, we end up on a new level of utility. Thus, we have changes in consumption. Now, what happened if we had changes in consumption here? Well, first off, what did the interest rate do? Did it increase or decrease? That's right, it increased. So if it increases, well, we were initially consuming at C0 or CT0 and CT plus 1, 0. But the interest rate increases. So when that happens, we consume less today and we consume more tomorrow. So that brings us to this point here. So we're now at a higher level of utility with changes in our consumption patterns. Okay. Now let's assume for a minute that we were to stay on the same level of utility. How do we do that? Well, because we're not really, right? But let's just assume for a minute we are. Well, this line pivots, right? It pivots from the pink to the orange. And then what we would do is we just shift this line back in, just find a new parallel line that brings us back to our original utility. And this would be our what C1T and C1T plus 1. Now I've got S here. What is that S for? Well, that S is denoting the substitution effect. So if we're holding this level of utility constant, and there's a change in the interest rate, I'm going from C0 to C1. Here, consumption falls. And then over here, I'm going from C0 to C1. Consumption increases. So current consumption falls, future consumption increases. Now, why would we care about looking at this on the old level of utility if we're moving to a new level of utility? Well, it's because there are two effects to a price change. There's a substitution effect and there's an income effect. The substitution effect occurs when there's a change in relative prices and we go from consuming less of one to more of the other good, right? Then there's the income effect. The income effect comes from a change in real purchasing power, and that's where we get that shift in the budget line. Now, the substitution effect is always going to be negative. Always, always, always negative. The income effect can sometimes be positive, it can sometimes be negative. We can have an ambiguous income effect. Therefore, if the income effect ends up being larger than the substitution effect, well, we have a really strange situation here because if, say, the substitution effect, which is always going to be negative, we always know that the substitution effect will be negative. That income effect is positive and it's larger in magnitude than the substitution effect. Well, we have an ambiguous total effect. And that's why we've got this C2T and here, C2T and C2T T plus 1. That superscript T tells me it's the total effect of this price change. So I got the substitution effect and the total effect. The difference between the total effect and the substitution effect is the income effect. That's the change in real purchasing power, hence why the budget line shifted out a little bit. I know this is kind of complicated. Please bear with me here. So if we stay on the same indifference curve, kind of like as a thought experiment, following that relative price change, that reallocation of consumption is explained by the substitution effect. And it's predictable. We like to think about things in terms of that substitution effect because in order to stay on the same indifference curve, you have to consume less of one good to get more of the other. Remember that whole proof I showed you where the indifference curve was downward sloping, right? Well, in terms of the substitution effect, that is why we needed to see that. So when we have this like new allocation, well, we move to a new indifference curve and consumption changes again. The amount that changes by is what's known as the income effect. So we have these two effects here. We have the substitution effect and we have the income effect. And anytime there's a price change, you will have these two effects that are moving. Sometimes they move together, sometimes they move in opposite directions. If they move together, hey, cool. If they move in opposite directions but the substitution effect is still larger, okay, well, a little less cool, but still cool, I guess. You can still kind of get some idea as to what's going on. If they move in opposite directions and the income effect is larger in magnitude, well, then you got a problem. Yeah, that's when things can get kind of strange. It's actually where you get what's known as a Giffen good, where you can end up with like an upward sloping region of the demand curve. Really weird stuff. So sometimes the income effect can overpower the substitution effect. Sometimes it doesn't. So we like to kind of think about things in terms of just the substitution effect here. And really throughout a good chunk of this course, what we're going to be doing is we're just going to assume that there's a substitution effect and that there's no real like income effect. Maybe not the most realistic assumptions to make, but hey, this is intermediate macro. This is not like PhD level macro theory. I'd like to keep things kind of simple for you guys. So we saw how to analyze indifference curves, and I guess we can end the chapter on that and move on to the neoclassical growth model. And now that we've learned some dynamic optimization stuff and moved on to the neoclassical growth model, it's really going to take mostly things from chapter 5. Chapter 6 is just a way to envision what's going on in chapter 5. But we're taking chapter 5 and we're applying it over to the solo model, which then improves the solo model. So yeah, that's enough of that for today. Thank you for watching. And be on the lookout for the neoclassical growth model.